plus the formula that are presented here for you for the 2m coefficients, and yeah, for the effect of this you can compute the corrections. Of course they have computed how to derive this phase element, but you will just need to learn how to apply. That would be fine. So you will use this table to consider the effect of other components, the frequency. That's for the solid type. And we go for ocean type, the same document. Yes, you have the formula here for the ocean type. This is the correction to the sine coefficient, this is the correction to cosine coefficients. And theta, you already know it. We have discussed that. And these are the spherical harmonic coefficients that are from the ocean type models. So how do we do that? We go, this formula is theoretical, but the background, this part is important, that it comes from a spherical harmonic expression. And look at this expression for them. Here you have sine and cosine coefficients. Theta f you have already known. These coefficients come from the ocean tide models. Ocean tide models. And xf has a formula to compute. You see. So we have, based on this phase bias, it's called phase bias, we can determine that. The ocean tide models, you have different ocean tide models. You can use this for computing them. Yes. Then you have the amplitude, and these are the symbols for symbols of the tidal component. So in this way, you can determine the effect of the ocean tide from the ocean tide models on the spherical harmonics. And here you have load numbers too. So yeah, this is also the formula for the ocean tide model. For the sine coefficients or cosine coefficients, and you can use them in practice for practical. This is shift of the phase. This is the phase, I think. Let me check it. Not even here. See, phase. Yes, it was phase. These are from the model, and these have load numbers here, and you can compute these CMF coefficients. And the ocean tide effect on the spherical harmonic coefficients, which is here. Yes, yeah. This is the main formula for computing ocean tide. So we can have a separate course for discussing about the solid tide and ocean tide. But as you see, considering solid tide and ocean tides is more complicated because there are lots of geodynamical parameters inside based on the rheology or the structure of the Earth. It's not that simple as a direct effect. You will compute corrections to the spherical harmonics of the gravitational potential that you use for computing the geopotential acceleration. And you will correct this. If you want to determine the orbit, you will compute these parameters, these coefficients inside its coefficient and add them to the geopotential coefficients. Or when you compute the spherical harmonics, you can compute these effects and remove them from the computed spherical harmonic to make them free of ocean tide. That's the way. Then let me come back to this. So, how can we explain this? I said that ocean tide, solid tide, ocean tide. I write it like that. Corrections to V and M, both. So what can we do then? Let me write this equation. So gravitation, we had transformations, we have gradient of the potential plus direct tide plus indirect tide. Indirect tide and plus one is general relativity. So as I explained, if you want to determine the orbit, you want to determine the acceleration and solve this differential equation to get the orbit to come to the position and the velocity, you will keep them here. Otherwise, if you want to determine the potential, then they should go there. They should go there, and this part will be unknown parameters for you. The transformation is known, and this one is unknown. You will get this acceleration. And from the acceleration with vector spherical harmonics, and you can, for this least square principle, you can estimate the spherical harmonic coefficients. So for the relativity,